So without further ado, Mr. James Shubin, aka Purple Idea.
Hi everyone. All right, I'm going to steal 5 minutes from Hitoshi's talk, but hopefully I'm going to try and get through everything. So if you have questions, raise your hand if it's really important. I'll try and do some at the end, but I really have a lot of demos, so I want to show you this. Let me just kill this video. All right, so really quickly, I'm James. I go by Purple Idea on the internet. So if you like this presentation, you can like tweet Purple Idea that it's awesome and that it's the best thing you've ever seen and so on. I'm actually going to sit for part of it so I can type, so please excuse me, but I'm still here hiding behind this thing. So just really quickly, who am I? I'm a hacker. I work on config management. If you guys can turn down the mic ever so slightly, it would be great too, because I have a bit of a cough. So yeah, I work on config management. I write this technical blog. And I'm actually a physiologist by training. So if you actually want to talk about cardiology and you want to nerd out because you're sick of computers, I'm happy to talk about this. It's really great stuff. And I'm definitely a big DevOps believer. And as a DevOps sort of believer, I kind of end up having to write tools to actually do the things that I believe in. And that's what I'm going to talk to you about today. So I don't know if anyone's remembered some of my old Puppet hacks. Puppet's a config management thing. If you haven't been familiar with that, you might be lost a little bit. But they basically went like this. I think the monitor sound is off. There's actually a screaming noise that comes out of the computer right now, which is Beaker going, whoa! But anyways, so some background. I started hacking with early Puppet, fairly early Puppet. I think I got pretty good at it. And I wanted to do some things that were a little bit outrageous. And I gave some presentations about these things, which I think is where I started to get a little bit well known in the config management community for doing these things. Here's actually recursion in Puppet. Does anyone know you can do recursion in Puppet? Come on, don't be shy. Felix knows because he's seen my talk. But everyone else, yeah. It's not a good idea, but it's something you can actually do. Here's a little thing that actually, you run the command, and it actually decides when it should run again. And it spawns off this little Python thing that double forks away from the Puppet process and then reruns Puppet when you need to run Puppet again. Good idea? You guys are shy. Good idea? No, not a good idea. You can actually build timers in Puppet. So I actually built timers. So you can actually decide to say, boot up your DRBD cluster, wait an hour for the machines to converge or to replicate the DRBD, and then run something again to finish building the cluster. Code there if you want, but it's kind of scary. And you can actually build a finite state machine in Puppet, which was kind of an outrageous hack I did to prove that it was possible. Just sort of feeling what you can do and pushing the limits. Is this the right way to do it? Do you like this? Come on. All right. So this is my, is this the right way to do it guy? I don't know if you've seen him. And he's just like, nope. Have you seen this? If someone wants to record a soundtrack to go with this video, that would be amazing. Please email me. All right. So what I did is I eventually sat down and I started building what I think the right thing would be. All right. And so it's called Mgmt or Mgmt config or whatever. I'm really shit at naming, so I'm really sorry about that. But let me explain to you the basic design principles, and then I'm going to show you some demos. It has three main features that differ it from Puppet and other things. So the first thing is if you look at your graph of all the resources, it runs everything in parallel instead of one at a time the way Puppet, for example, does. Excuse me. The whole system is event-driven, which I'm going to show you shortly. And lastly, and particularly at this conference, the whole thing works as a distributed system, and it uses etcd to do that. I'm going to show you that shortly. So we're going to go through these 3 points with some demos. So this is a typical resource graph that everyone's familiar with. Yes? Yes. All right. Someone is here. So what you typically do is you have all the resources, and what actually happens is Puppet will do something called a topological sort. And if you look at the red arrow, can you see the red arrow here? What it basically does is it orders them in a way. So 1, 2, 3 will run, 4, and then 5 and 6 and 7. But if our engine could actually run in parallel, you can actually run it like this. So you can actually run the entire left half at the same time as the entire right half. And actually inside of that left half, once you have 1A done over here at the top, these two can both run in parallel. You wait for them to both finish, and then 3A runs. All right? So here's the demo. Just a very simple graph that I'm going to show you. These are just little exec resources, and each of them is going to run the command sleep for 10 seconds. So it's not very exciting. And if it runs in parallel, how long is this going to take to run? Louder? 30 seconds, right? So these 3 are going to run at the same time. We're going to do a little just demo of this. I just have all my little demo notes. So just to show you how this works, I'm going to actually run it, But I have this, let me see, can you see that okay? How's that? Yeah. I have this little converged timeout option. So what happens is the engine is going to start up, and it's going to run. It's going to run continuously, but once the graph has converged, that is, everything is in the correct state, for, in this case, 5 seconds, which I put on the end, it's going to quit. All right? So it should take 30 seconds plus 5 to converge, and we're going to time the whole thing and see it run. All right? So live. So we run the thing, it starts up. There's a lot of debug garbage and crap all over the screen, so my apologies. If you look here at the bottom, exec 1 and exec 4 both start up at the same time in parallel, right? At about 21 seconds. 31 seconds, which is 10 seconds later, 1 and 2 both finish, and number 4 starts up. So 4 is running, 10 seconds are going by. You finish, 4 ends right there, and number 3 right here at the end is starting up. You can see it apply. It's just a sleep command, so there's no command output, but you get the basic idea. Lastly, 10 seconds later, the third command ends, 1, 2, 3, 4, 5, and then the whole thing shuts down. And if you look, it took 35 point something seconds, right? So basically the tool, it's running in parallel and has virtually no overhead, right? The only CPU resources you're really using is to run the resources. And in this case, it was nothing, or very little. All right? Any questions before I continue? No? Who is shy? Who's really shy? Okay? Who doesn't like raising their hands at conferences? Anyone? All right. Some people in the back are like, please hide me. Yeah, is it a German thing? Oh, scheiße. Okay. Anyways, so this is that first graph. I have a similar graph here, but I'm not going to show it just for time. It does about the same thing, and it just parallelizes that way, so you can see it. Second part I want to talk about is this event-driven thing. So anyone who's familiar with Puppet, Puppet runs every, say, 30 minutes. So it runs, it starts up, it loops through, and then it ends, right? 30 minutes later, something happens again. But what happens if something gets out of convergence in the middle between runs? When are you going to hear about it? You're really shy. You're like my most shy audience ever. Yeah, so it will only converge or get fixed the next time you have a Puppet run. So if we could actually respond dynamically to events and immediately apply this, the second something happens, we can have a much more efficient system. And I'm going to show you a demo of this. The way we do this actually is by watching, in the case of file resources, we look for events from iNotify and FA-Notify, for example. For services, we look at systemd events, kernel events, package kit events for package installation removal, and so on. And let me just give you a little demo. So I have a little, so I'm going to show you a very simple demo right here. What basically happens, now this is YAML to describe the code, but that's just temporary for hacking. But I'm going to tell the system to build 3 files, Mgmt F1, F2, and F3. And each of these files will basically say, hi, I'm F1, I'm F2, and I'm F3 in the contents, all right? The last file, temp Mgmt F4, is going to be state absent. So I'm going to say, please make sure this file does not exist on the computer. Okay? And so we'll just go over here. Let's go into temp. Can you see that? Okay. We'll go into here. There's nothing in this folder. Nothing up my sleeves. Not funny. But so I'm going to run the thing. And so immediately we run it. And it's already done because it didn't really, you didn't even see it finished, but it finished basically right away. And if you look, you see those 3 files are there, and they all have what we expect. Now that's not very exciting because we can actually do this. We can actually remove F2, and then ls, and you can see right there it's back immediately. On the left, you see the system working, so we'll just do that again. Boom, it's right back. And it actually works so quickly, you can actually do rmf2 and cat f2, and boom. And you can just do this over and over again, and the system is always going to respond immediately to do this. And if you really want to like troll your sysadmin or something, you can actually run this in watch. So watch is a little program that runs things as fast as possible, and 0.1 is the fastest it runs at. And if we actually just run this in a loop, you'll see that as soon as it deletes it, it immediately puts that file right back. And on the left, you can see the system spinning away. All right? And you know, obviously you can do things like, you know, CoreOS fast is awesome, and put that in F2, and you know, you can see that it obviously fixes it, all right? So really confusing if you're wondering what's going on in my system. Hey, I deleted that file. And you know, naturally also if you make this file F4, it gets deleted. So touch F4 and file F4, you'll see that the file has always disappeared before it's gone. Is anyone confused so far? Everyone, questions? No? This guy's got a big grin on his face, so I think he's like, yeah, I like this, right? So imagine like real-time configuration management for your system. So we're going to kill this. I'm going to show you some more demos, or you've had enough? Yeah? All right, cool. All right. So, so what is this actually? Does this look like anything else to you? Does this feel like something else? Because I told you it was config management, but it's a bit of a sleight of hand. Does it feel like something different? The guy with the smile on the back, another smile. What does this feel like to you? You're on the spot. It's okay. No, there is systemd events for services, but what I'm really getting at, I'll give the answer away. I actually think this is actually kind of monitoring. So if you think about it, we just have simple resources for files and services and packages, but if you build more and more complex resources, you can actually sort of have a monitoring engine the same way you would have, say, sort of Nagio sort of thing. So instead of having config management, and then after you've deployed your app and built your infrastructure, then you put monitoring in, have it all be integrated together into the same code base. And this will hopefully make it a little bit easier. And on top of that, you can have natural monitoring pathways that show you what to do when something goes wrong, and declaratively in code. All right, so the last thing I really want to show you introduction-wise is how the system actually works topology-wise. So this kind of topology is what? Client-server, right? So this is the sort of thing you're familiar with Puppet. You have a whole bunch of clients. They go off and contact the server, and the server replies and so on. What are the problems with this topology? Single point of failure. What else? Not scalable, and so on, right? Let me show you a different topology. This is the sort of orchestrator Ansible technology, topology, if you want. Same sort of thing, except here the orchestrator, so when I say orchestrator, orchestrator in my words means central orchestrator. And a central orchestrator initiates to the machines that it wants to manage or do things to. So what's the problem with this topology? Don't be shy. Don't worry, if you're wrong, it's okay. What? It also doesn't scale, and it can be a single point of failure, right? So these are useful topologies. They're very classical and well understood topologies, but I think there is actually room for improvement. So this was sort of the initial idea for the distributed topology, but very quickly you can tell me what the problem is. If everyone is a peer to everyone else, what happens that causes you a big problem? It doesn't scale, right? Because if you have 6 peers, the number of connections is huge, and if you have 100, just forget it, right? So what we actually do is something actually that looks a lot closer to this. We have as many peers as you want, or you have some large number of peers, and what you actually do is the cluster itself automatically or autonomously, I'm not sure which one, but both of those will elect temporary masters to be etcd servers, and everyone else will connect to those machines. And I'm going to actually show you a demo of this. And this cluster actually has a distributed key value store, which we use inside of Mgmt. And that's what I'm going to show you working first, and then I'm going to show you the cluster management. All right? So the demo I'm going to show you 3 nodes. They're all going to run on my laptop, but you can imagine they're running across different machines. A, B, and C. Each of them is going to create 2 files. And Puppet has this concept of exported resources. In case you're familiar with it, do you know about exported resources? Yeah, some people yes, some people no. If you don't, that's okay. Exported resources actually I think is a very nice design, but I don't think it was put together nicely, and particularly because there's no events and something like that. But this is actually sort of quite familiar. So what actually happens is each machine is going to create 2 files, and one of those files is going to get pushed up into this distributed key value store, the information about that file. And then the second thing that's going to happen is the client, this peer, is going to pull down all of the file information that's there. So this is my crappy little drawing that I made. Each has 2 files. It pushes this sort of virtual file up, and those get realized, they get pulled back down, and then they get created. All right? So hopefully you'll see this in a moment. But basically, if you think about it, if you have 1 file on each machine, you push it up, a copy of that, and you pull everything down. How many files do we have total on each machine? 2. So you have, each one has the 1 file here. It pushes it up into the cloud, or the key value store, and then since they've each pushed up 1 file, there's now 3 total, and each one pulls those 3 back down. So you'll have the original one plus 3 more. All right? So let me show you in action. It'll be a little bit easier to follow. Oh. Okay, this is my little notes of what I want to demo here. All right. So, oops. So I'm just making little directory for these things. So you can see 3 directories, which represents this file storage on each machine. And just for fun, we can actually just watch it so you can actually see live what's happening. So this is what's in those folders in real time, pretty much, if you want to see what's actually happening. And here we're just going to run these 3 servers. Now normally you would just start up everything, but because I want to show you actually stepwise how this happens, I'm going to show you one at a time, all right? So I'm going to start up the first one. And it starts up, and then instantly, basically, you see it puts those 2 files. So it puts one on itself, and it pushes one up into this cloud, which then gets pulled right back down, therefore 2. All right? Start up a second machine. The second machine, so we're going to start it up. How many files is it going to have after this runs? 3, right? Because it has one more that it pushes up, and then pulls those right back down. So we'll run this. Boom. I don't know if you even saw it switch, but now 2 has 3, but also that first machine saw that there was a new file up there, and it instantly responded and pulled that file back down. All right? So it has 3, and then just for fun, we'll start up one more machine. And this one I'm actually going to run slightly differently. I'm going to run it with that converged timeout thing so that the machine actually shuts down after it's converged. And this way you'll get to actually time how long it takes. So if it's a 5-second timeout, anything bigger is the actual time it took to run. All right, so 3 files on each machine. C is going to add one more file into the pool. So how many files will each machine have? 4, right. So let's run it first of all. So I run it, boom, it instantly responded. Each have 4 files. 5 seconds go by, and then boom, if you can see here at the bottom, 5.0 some odd seconds. So the thing is really, really fast in distributing all this. Now you might ask, like, what is this useful for? It might not be super apparent at first, but with this very simple pattern, you can actually do some very complicated things. For example, if these were web servers and you had a router somewhere, when the web server starts up and opens a port on its local firewall, it could actually send this exported resource up to the router server, which would say, router, please open the route so that traffic comes directly to me. And when your web server stops or shuts down, you could close that port, for example. With a distributed file system, if you wanted to manage that, you would automatically be able to see which peers are in the system and cluster them together because you have this back-end technology doing that membership and all of that coordination for you. So there's a lot of patterns you can do, but this is just the fundamental core stuff that we build on. Okay? Any questions before I go on? Don't be shy. If you have a question, happy to take it. There's stickers for really good questions from my private sticker collection. Any questions? Last chance? All right. So that's my, if someone knows how to make better pictures, like, please let me know. You don't have to contribute code. You can contribute LibreOffice pictures. So I'm going to show you a few more features. That's the base stuff. So the first thing I want to show you is elastic cluster management. So each machine, actually, as I said, embeds the etcd server, and it will automatically decide in the cluster who should be promoted to a server and who should just remain a peer. And if you have all these, say in this case, these 4 peers in the middle, and one of them dies, and you want, say, at least 4 peers running, you can automatically re-elect a new machine to come take over. Cool? And I'm going to show you this demo. So let's do this. So the way you do this, actually, let me just actually kill this existing. Okay. We're just going to kill the existing servers. So the first one we're just going to start up. Starts up, it's running, and so on. The first server that you start up, you just say, you're the first server, start up. The way you actually get them to cluster is you only have to tell an existing server or an existing Mgmt agent the IP address of anybody in the pool. So you give it the IP address of any other existing machine that's running, and it will automatically elect itself. So that's what I'm doing right here. If you actually see the command that I'm running, I'll just run it. So what it actually does, I just tell it what host name I want it to have, and I give it the IP address of the first machine. Okay? You can give it any machine, but right now there's only one machine, so quite simple. These other 2 client URLs and server URLs are the IP addresses that I want it to run on. So I only have to specify this because I'm running all on the same machine, and the ports would crash, collide. So that's why you specify those. But normally when you're doing this across machines, you don't have to. So I'm just going to run that. and then boom, instantly they cluster together. If you don't believe me, we can actually run tcd-ctl, oops, and just look at the member list, and you actually see there's 2 peers right now, all right? So let's add another one. Should we add another one? Yeah, why not? I have resources. I have the RAM. So we'll just add another one, run it, and boom, instantly, they're clustered together. There's actually quite an algorithm that happens that makes this all happen. So you don't see this happen, but I can explain it to you if you're interested. And just for fun, we can see, now we actually see H1, H2, and H3. They're all peers in this cluster. Now, I've actually told the cluster, I've hard-coded it to say, I want 3 machines in the cluster. Now, in the future, we'll be able to have an algorithm that decides how many you want based on load or whatever it might be. But at the moment, it's just hard-coded to 3. So let's actually start up a 4th one and see what happens. So here's the 4th one we're going to start up. Okay, we'll just start up number 4 over here. And it starts up, but it does not get added to the cluster. And the reason is because we're already at the maximum. So we already have 3 machines in there. But if you were to go and say, take machine number 3 here and kill it, you'll see that what it did is actually automatically started up the 4th machine, which you can see right now. So now, oops, why didn't that work? Did I kill something? What's going on? Huh. Did I? There
was a bind address in use.
Yeah. I might have used the same, I might have copy-pasted wrong. Let's just start this guy up. So H2 right there. So 2nd machine is up. What did I do wrong? So there's actually one small race condition that I've been chasing down, which sometimes gives me a bit of hassles, but I'm going to try and get through this. So A, B, C. I think it should work. We'll try it. Golang takes forever to compile these days. All right. So, first machine starts up. There we go. All right, and then this one, H2, starts up. It should cluster together. H3. So H3 just started up like this. Okay. Let's start up H4. H5. I think it looks good. Okay, so all the peers are there. All right, and let's say we kill one of them. Oh. Let's kill one of them, and you can see that, there we go, yeah. I think I copied paste something wrong. So H1 and 3 and 4 are now running because 4 replaced the 2nd one that was missing. And we can actually start up number 2 again. Nothing will happen until we kill some other machine, and then that will take over its spot. All right? So that's true elastic cluster management. There are actually some bugs in this. There's a small race because to do some of the membership changes, I actually need to use the raft log, which I'm not doing at the moment. But so this will require some upstream etcd changes, but hopefully I'll be able to write these, or someone will help me write them in the future. Any quick questions on this before we continue? Yes?
One question,
Yeah.
The election of the master is not dynamic. You actually peered it. I mean, you define the relation between the client and master.
So what actually happens is when you have the first machine that starts up, it starts up as nothing because it doesn't know about anyone else, and it says, well, no one else is here, therefore I'm going to be the master. Okay? The second machine joins as a client, and the client says, hi, I'd like to volunteer to be a server. Whoever the current master is says, okay, I would actually like more servers in this cluster, therefore I nominate you. And then when this one sees the nomination message, it starts up and joins as a peer. Same thing with subsequent machines. And that's how the algorithm actually works. If you are an algorithmist and you find problems with this, please let me know. I don't have Diego's skill at distributed algorithms, but it does seem to work. And the real goal is for me to build the stuff on top of this. So if we did get something wrong, hopefully it's a completely free software, open source project, so you can look at the code and fix it. Oh yes, it does, absolutely. Yes, and that's that. I'm going to just kill all these. Good. got a little bit more time. So that's the demo. You can add and remove machines as you like. Now, obviously, there's no guarantee that if you have 100 machines in the cluster and you like kill them all, you're going to have problems, right? So you have to always make sure you have a threshold of a minimum number of machines running for this to keep working. And that's just common sense. But as long as you do that, as long as you maintain that there are working machines in your data center and they boot up and do this, you should have no problems. I mentioned this, and I was really actually impressed. So I read a lot of etcd code, and it was kind of like hard. But I'm really actually quite impressed because to actually implement what I didn't really have to make any changes to the etcd core code to embed the server, which was really great on their part, that the things that I needed to be public, and I only really had to implement one small method to start the server. So thanks, etcd people. Patch review wanted, so if you want to, I'm going to clean up this patch and post it soon. So if you do want to help review this, please ping me. Do you want to see a few more demos? Yeah? All right, cool. So another quick feature in Mgmt is something called automatic edges. So if you think about Puppet, you have this sort of typical package file service pattern that you see, right? You have a file that represents some configuration file, you have a service, and you typically always have to do these like requires. So the service requires that the package is installed, and the config file requires that too, and you want the config file there before you start the service. You know, putting all these dependencies. So I thought this was kind of ridiculous because we have package managers, and package managers tell us that there is a service file inside, right? And they tell us that there's a config file that goes in a certain place. So what we actually can do is we can actually automatically read the package data from, you know, dpackage or RPM or whatever you're using, and automatically add these relationships, these edges in the graph. And you can do it for more than just these sort of resources. So I'm going to show you a quick demo of this. It's not as impressive, but it'll hopefully just show you how it works. So I'll make this a little bit bigger. So this is a very simple, very simple graph. It's going to have a drbd utils package. There's the config file, etc drbd.conf, and the directory, and the service, right? And I haven't, let's just run it and we'll see. Type my password, which is password. Okay, so now the whole thing is not going to run to completion because I actually have not implemented the directory part of the file resource yet. But so the point I want you to see is actually right here. So when it analyzes the package, it actually can automatically determine what relationships are necessary. And you'll have to trust me right here when you see, so the package happens before the service, right? Because we typically want the package to be installed and then the service that it contains to start. So this will automatically happen for you if you use this tool. Same thing, the package will always get installed before the configuration file is present. Because if you put the configuration file first, and then you add the package, some package managers put like an RPM new file or other stuff there. So that's added automatically. And same thing with this other config file. And all of this happens completely automatically. If you don't want this for some reason, you can disable it per resource. But by default, we think it makes sense that let's make your job as module writers easier and just automatically add the dependencies that we can infer. Make sense? Questions? My most enthusiastic attendee in the audience right here. Felix has a question.
Yeah, so you still have to specify that when the config file is changed, that the service needs to refresh?
Great question. So Felix's question is, when the config file is changed, does the service need a refresh? And the answer is that when the relationships are specified automatically, the system automatically detects this and will do that refresh for you. You don't have to do it. And the reason it does that is because those events that watch the file, when they see that something has changed, they say, oh, something has changed, and I'm going to reload the service. So you don't have to specify this. And it's actually quite an elegant thing. If you're familiar with Puppet, you know that there's the before and requires pattern, but there's also the notify subscribe thing to tell a service to reload and so on. But because these two are actually, because it's all event-based, you do not need a notify subscribe pattern because this all happens automatically. So there's no notify keyword, there's no subscribe. Yes?
That edge wasn't added, right?
Which one? Between the file and the service? Right, in this case, there's no information about that, so that wasn't added. But yes, if you add the edge, it will reload automatically. Yeah. Let me show you. Yeah, so this is only used for package resources right now, but in the future you can imagine if you write a new resource that has other parts that it uses, that you could add dependencies automatically. And there's a Golang API to do this. One other thing I want to show you, a feature I've called it automatic grouping. So here's some graph that we have. We have 3 packages, a service, and 2 files. All right? And so what's the problem when you run this with Puppet? Anyone know? What happens if you were to run this graph? What actually happens, yeah, someone? I've got stickers, no. What actually happens is that since everything runs one resource at a time and it doesn't run in parallel, it will actually start up the package manager 3 different times, one for each of these blue packages. Which is kind of a waste because a package manager, when it starts up, it has a fixed cost just to start up and check the caches and contact the network and so on, which is a huge waste of time. So what we can actually do in Mgmt is automatically, when we compile the graph, we analyze it with an algorithm that I can describe if you're interested, and it actually groups together certain things that we think can be grouped together for better performance. The one that we do automatically is packages. So packages are much more efficient when you group them together because you just do one big transaction. And I'll actually give you a demo of this if you want. Oops. Auto group 2. So this one is going to try and install those same 3 packages. I think they've been erased. And we're just going to run it. So we run it. It starts up. And if you see, it happened quite quickly, but it actually grouped all 3 of these packages into a single transaction, and at the bottom, it's actually installing them right now, and you can see the internet's going to download the packages. And obviously, the package manager still takes time, so you have to wait for that. But while this is happening, other parts of the graph can be running in parallel as long as there's no dependencies. Let this run. And the cool thing we can do, wait for this to install. The internet was a little bit, if you're torrenting, please stop torrenting, but, or at least share the files. So it will finish in a moment when the internet downloads the file, and then after that I'm going to remove one of the packages and you'll see it respond. While that's running, I'll actually just show you some other things. So the other kind of resource we can actually group is you could actually automatically group file resources to share iNotify watches. So if you have a whole lot of file resources, like a large number, you can automatically group so that iNotify watches, which are monitoring these things, which are a limited resource, you don't run out. And there's whole lots of other things that you can probably imagine that use this sort of thing. So if you have some sort of resource that makes API round trips to a server, and you don't want to do hundreds of these, grouping will actually do this automatically for you. Let's see, it's not done yet. And if you have other ideas. I actually took some data, and you can find all this data on my blog. So this is actually, if you see 1, 2, 3, 4, there's 4 different runs. And what I did is the bars represent the time it took to run the tool on reasonably working internet. The different colors are different tools. So the red thing is Puppet, blue is Mgmt, and yellow and green are the DNF package manager just running on the command line, and pkcon, which is the package kit CLI. And if, oops, let me just go back. And if you look very quickly, so this first one is just a single package installation. And if you look here, this last one here is a 3-package installation. And the more packages you have, you can see that the bigger difference between Puppet and, say, Mgmt is. So the longer the bars, the slower things are. So you can see actually that Mgmt, by grouping these things together, gives you a pretty big speed up in terms of how long it takes your packages to install, for example. And with any luck, yeah, so the internet's not working here, and it don't seem to be installed, but it's a little too bad. Let's see. There's always one internet demo. Internet seems to be working. Let's see. Come on, internets. If the internet goes, you'll see this install. If you want to try this at home also, you can just run this thing, it'll install the package, and then just randomly remove a package, and it will instantly notice that the package is missing and try and reinstall it. I think I'm almost out of time, so I'm going to have to wrap up. Yeah, I got just a few minutes left. So really quickly, some future work. So there's actually no DSL to specify this. So right now, everything's still in prototyping debug mode. And to specify resources, you just enumerate them in the YAML file. So at some point, we actually need to build a language, unfortunately, to do this. Felix actually had this idea to take existing Puppet code and cross-compile it to run on this engine. And Felix over here started working on that. So that's one way you could use existing code that you've already written with this new engine. But there are a lot of features that are going to be, I think, quite powerful that will, unfortunately, probably need its own language. So that's going to have to come. New resources. So if you want to write a new resource to do something powerful, think about with the event-based thing what you could actually do. There's a gentleman actually from Endocode who's actually working on a libvirt resource. So if you think about declaratively managing a virtual machine by just specifying, I want this virtual machine, and whenever you change the settings of the machine in your config management tool, it'll automatically fix that and make that happen. So timer resource, all sorts of things, network resources, all of these things need to be written. So if you want to become famous, practice your Golang, and get professional patch review, please ping me. I mentioned there's a few etcd things I need to fix up and work on. And the other thing that's planned, but I haven't started writing yet, is if you want to think about Ansible has this push mode, this agentless thing, you could actually imagine where you run the tool from your laptop, it pushes the binary over to the machine you want to manage, it runs, and then shuts down and deletes itself when it's done using. So if you don't want to run it as an agent, it can converge timeout and just stop. So this is something that to work on. And this is really a community tool. I do work for Red Hat, but it's not a Red Hat product. It's just really an upstream thing that I'm working on. And if you have a company and you want to sell this or sell support for it, go crazy. I mean, I'm here to support the upstream. So just please ping me. How can you help? This is about you. So you can use this, you can test it, patch it, share it, document it. You can star it on GitHub if you're into GitHub stars. You can blog about it, tweet, discuss, and just hack on this stuff, right? This is for you to build a tool that I think is quite powerful. If you're into containers, I know there's a lot of container stuff here. You might think of writing a container resource to see how you could schedule things that way. I mean, there's lots of options. I have one marketing slide just because Red Hat paid to send me here, which was kind of nice. Thanks, Red Hat. And it's an upstream community project. It's not a product. So you can't buy this. Don't ask your salespeople. Come to the upstream, and it's all free. Let's just recap. Guys in the back, the sound has been cut off from the laptop.
Thank you.
There we go. I'll start it over.
Answer. Now let me recap.
This is the recap thing. Have you ever seen this guy? Arthur Benjamin.
Thank you.
Recaps the pen. I don't know, it's a stupid joke. Here's some links for you. Technical blog of James, Purple Idea on GitHub, Mgmt is the project. I see some phones, but I'll post the slides on Twitter if people want. And you know, this is a funny thing that my friend sent me, which I thought was kind of funny. So I'm pretty much out of time. If you have questions, I'll be around here and I'll also be at the evening party. Thank you very much, and please let me know what you think.